Hello, everybody, and welcome to another session. Today, we will be taking at a few computational experiments that I had carried out on the Goldbach conjecture a few months ago, and I wish to share some of the work that I've done. The Goldbach conjecture is a simple conjecture stated way back in the 18th century, which says that any even number greater than or equal to 4 can be split into a sum of two prime numbers. For example, you take the even number 10, you can write it as 7 plus 3, right? 7 is a prime and 3 is a prime. Or you can take the even number 102, you can write it as 89 plus 13, or you can write it as 97 plus 5. So either way, you're splitting it as a sum of two primes. So this is what Goldbach had claimed. And the interesting thing is this conjecture is yet to be proved. People assume it to be true. It has been verified up to 10 to the power 17 or something like that, but nobody has actually come up with a proof, although it actually works for every single even number that has ever been checked on. So I tried to play around with this conjecture a little bit, and I wish to share with you some of the things that I came across, which I find slightly amusing. So let's take a look at this paper, or not this one. Yeah, this one. So this was written way back in fall of 2020, and what I did was I was looking at a certain paper written by another mathematician called Laurent Hodges, and he had done a few things on the Goldbach conjecture, and I wanted to write a little bit of a commentary on his work and try to come up with more examples for some of his claims. Because what happened was this paper written by this mathematician was way back in the 90s, when I don't believe he had that many resources at his disposal or the computational speed to come up with a lot of examples. So I just wanted to try it on a modern machine and see if we could do a few things with the Goldbach conjecture. So what he did was that he worked on something called the Goldbach's lesser known conjecture. So we all know the Goldbach main conjecture, the one which I told you, that every even number can be split into a sum of two primes. But Goldbach also had a second conjecture, which is very little known, and it's called Goldbach's lesser known conjecture. And this is the current statement of the conjecture. So he says that every odd number can be written as a prime plus 2 times a square number. Okay, so this is again very similar. The logic is very similar to the first Goldbach conjecture. The goal is about splitting natural numbers and trying to relate them to primes in some or the other way. So here what he's saying is you pick any odd number, and then you can split the odd number as a sum of a prime and the sum of double a square. Okay, I think most of us here have seen these kind of conjectures in number theory, but this is a little bit new. And the interesting thing is that particular conjecture has two contradictions. It doesn't really work all the way. It has two contradictions. This odd number 5777 cannot be written as a sum of a prime and twice a square. 5993 can also not be written as a prime and sum of prime and twice a square. So it's a little bit of a weird conjecture because it has contradictions. But in the totality of things, I would consider these numbers to be really small. So I mean, if I was Goldbach, I would just say this works for every number beyond 6,000. You guys might recollect I had made certain similar claims when talking about Rn numbers, where I just said this works starting from 5,400 or something like that. So these are trivial, very small examples, and I'm sure there's nothing else all the way up to whatever has been checked, which would be beyond 10 to the power 15. So what he did was so let's look at some of the things that are written in this paper here. He wanted to come up with solutions to the conjecture, and what he defined a certain sequence. Okay, and he defined a sequence where, so right now we know that every odd number can be split into a prime plus twice a square. He wanted to come up with a sequence where the nth term of the sequence can be written as a sum of a prime and twice a square in n number of ways. So rather than just saying it's a prime plus twice a square, maybe we can do it in 2 ways, maybe we can do it in 3 ways, 4 ways, right? So this is the sequence, and he had only written, I think, the first few terms, but I actually ran a code that took it all the way up to the 500th term of the sequence, because the program ran for like 3 months. My entire semester the program just ran. But let's look at these few first examples. So look at this. 3 is the first number, the first odd number. It can be written as a square times 2 plus a prime in only one way, I think. So he considers this as 2 times 0 plus 3. 0 is a square number, right? So you can write it as 2 times 0 plus 3. That's the only way you can represent this as a prime plus twice a square. The number 5 can be written as prime plus twice a square 2 times. Can we think of which are the 2 ways and put it in the chat? So which are the 2 ways in which you could represent 5 as a prime plus twice a square? Prime plus twice a square. Let's put it in the chat. We want to represent the number 5. Okay, good. So let me just enable chat for, oh yeah, I think everyone publicly is enabled. So you, Tanmay, can you just copy paste the thing into the public chat so that everyone can see your answer? Okay, I'm getting a lot of answers, but please try to put it in the public chat so that everybody can see your answers. Yeah, I'm still getting the private messages. Can you all just send that to everyone rather than just to me so that we can all have a look at the, okay, good. So the first thing is 5 can be written as 2 times 0 plus 5 because 0 is a square number, and you can also write it as 2 times 1 plus 3. Okay, 2 times 1 plus 3. Good. So now let's look at the next number. You have 13 over here. So 13 can be written as a prime plus twice a square in 3 different ways. Let's think of it. So one is 0 plus 13, trivial. The next would be 2 plus 11. And the next would be 8 plus 5. Okay, so this is the sequence. And I just ran the code all the way up to. So does anybody have any questions about this sequence? It looks like there are a few repetitions over here. Can somebody think of why we might have had repetitions in this sequence? Because we're having 6,319. Do you think this is a typo that I've done, that the same number is coming up many times, or could there be some mistake in the literature, or what do you think is going on? Any thoughts why the same number is appearing multiple times? No? So what happens here is that we are talking about a sequence, right? It is the first term, the second term, the third term, the fourth term. So what does the term of the sequence basically imply? If you have the 8th term of the sequence, then it implies that it is the smallest number that can be written as a prime plus twice a square in 8 different ways. So if a number is repeating, then basically it means it's the record holder for that as well as the term. So maybe this is the smallest number which has 14 unique solutions. It's also the smallest which has 15 unique solutions, and it is the smallest which has 16 unique solutions, something like that. So the same number will have the record holder for many different n's. So it will just show up many number of times in the sequence. So running this code for some time, and then I get this number which has 900 unique solutions. Look at this. 5,583,451. Now, the first thing that struck me with this discovery is that this number is really small. It's tiny. 5 million is a very small number. And if this number has 900 unique solutions, this conjecture probably has a very high chance of holding true forever. Because if smaller numbers are having these many solutions, we might expect larger numbers to have lot more solutions, certain larger numbers. Okay. The first number with 500 unique solutions is 1,437,679. So it just took something 5 times bigger to have 900 unique solutions. So technically the growth rate of the number of solutions is also relatively fast. It doesn't really take a lot of time. Okay, anyway. So let us forget that, and let's now come back to the original Goldbach conjecture. And I wish to share a couple of graphs here, which I think will excite all of you a lot. This is my first conjecture for this particular paper. Okay, and let us take out some time to understand this. So what I'm doing here basically is trying to give you guys some sort of a exposure towards seeing math in this form, because when I was your age, I found it really hard and annoying to read math when it was written using these symbols and with this font, and I was never really interested. I always liked to see numbers more than alphabets, and I like to see figures and facts and proper words in English rather than having some symbols and XYZ. So what I'm hoping is that when we take out some time and read these very slowly, maybe we will develop a taste of reading mathematical papers. Trust me, this is really a very stupidly written paper because it's written by me. So it's not really like a fully fledged math journal sort of paper. It requires a lot of editing. But I do think that it'll be a good start for all of us to start looking at these kinds of things. Okay. So let me just read out what I've written here. The popular Goldbach conjecture on even numbers as sum of two primes is equivalent to the following claim. Now this is a very dense statement, meaning it would take us some time to understand what this statement means. So let's actually study it very closely. What I'm trying to say here is I want to change the statement of the original Goldbach conjecture into something else. So what I'm trying to do, rather than saying the active voice to passive voice when you talk in English, or restating a certain statement to make more sense in a setting. So I'm just trying to take the original Goldbach conjecture and rephrase it without changing its meaning, just to make the same sense but to understand it better. So what is the original conjecture saying? Okay, the original conjecture is saying, let me actually use the whiteboard here. So the original conjecture is saying that if you have a even number, let me write it as 2n, you can split it up into a sum of two primes. This is the original Goldbach conjecture. Now we've forgotten the weaker conjecture and we're coming to the strong original Goldbach conjecture for even numbers. Okay. So take an even number, you can split it up into a sum of two primes. Let me write P1 and P2. So what I wish to do now is to rephrase this conjecture into something else. So how can we interpret this in a different sense? So let's look at this diagram. Let's think this is my even number. Okay, I know this is very abstract, but think this is my even number, which has a certain length. Let's say the length of this rectangle is the even number. Basically, Goldbach implies that you can split it up into two parts, where this would be P1 and this would be P2. Do you all agree with this analogy? This is what it's implying. Does this make any sense? You have an even number, you want to split it up into two primes.
Yes, sir.
Okay, very good. Now, a simple basic question. If two numbers have to add up to form another number, okay, can both, okay, first of all, this is an even number. So you all agree that this even number has a half, right? Basically, it has a midpoint. Since it's an even number, there's exact natural number midpoint to this rectangle. It's an even number. It's a multiple of 2. So you can split it into 2 exact halves. So it has a midpoint. If two numbers are adding up to form this even number, can both of those numbers be larger than the midpoint? Can both of these prime numbers be greater than the midpoint of the rectangle? Is what I'm asking. No, not at all. Because if two numbers are both greater than the half of the number, they add up together, they'll form more than the number itself. Okay. Can both of the numbers be smaller than the half of the rectangle? Can they be smaller? No, not at all. Because if both of them are smaller, you add them up together, the sum will also be smaller. So the only way possible to take up two numbers to add up to form another number is one of them should be larger than the half and the other should be smaller than the half. Do you agree with that? One of them should be larger than the half and the other should be smaller than the half. Can somebody give me additional information about this? In addition to just being on one side of the half and the other side of the, yeah, or both should be equal. That's also well and fair. But let's assume that they're not equal. Okay, equal is fine. That is understandable. Suppose they're not equal. Can you give me some extra information about how far they will be from the midpoint? So there is one number which will be greater than the midpoint and one number which will be smaller than the midpoint. Can you try to come up with a logic as to how far away will they be from the midpoint? Very good, very good. They should be equally far from the midpoint. You cannot have one number far away from the midpoint and the other number very close to the midpoint. They should be equidistant from the midpoint. Only then will they both add up to form that number. And this is not true just with primes and even numbers. This is just true in about any situation. Let's look at this. Let's take an even number. let's say 56. Okay, I will write 56 as a sum of two numbers. I don't care about them being prime or not. I'll just say this is 50 plus 6. Okay, I just claim that 50 and 6 are on equal sides of 28, because 28 is half of 56. Is that correct? 50 is 22 more than 28, and 6 is 22 less than 28. So they're equidistant from the half. You can pick any pair of numbers that add up to form an even number. They will be exactly far away, equally far away from the half of that number. Also, this will work even in odd numbers, but the half of the odd number will be a decimal point. But in any case, if two numbers are adding up to form another number, they have to be equally far from the midpoint of that number. Okay, so once we've established that, can I give you my version of the Goldbach conjecture using this logic? What Goldbach conjecture implies? It implies that for every single natural number, okay, not just even numbers or not just odd numbers, you take every single natural number, the Goldbach conjecture would imply that for each of those natural numbers, there exist two prime numbers, one on the greater side and one on the lesser side, which are equidistant from that natural number. For example, if your natural number is 7, you have 11 and you have 3. Suppose your natural number is 18, you have 23 and you have 13. So you can find two prime numbers that are equidistant from your natural number on either side. How is this implied from the Goldbach conjecture? Because the Goldbach conjecture states that every even number is a sum of two primes. Okay, so then what would happen is for any even number, you can find two prime numbers that are equidistant from the midpoint of that even number. Do you agree? If Goldbach conjecture should hold true, then it would imply that for every even number, you can find two prime numbers equidistant from its midpoint. Okay. Now, what would that imply? What is the midpoint of that even number? Well, technically, it could be anything, because this should work for every even number. Since every even number is 2 times a natural number, and you could pick any natural number, you multiply it by 2, you'll get an even number, right? You take a natural number, you multiply by 2, you get an even number. So if that even number is a sum of two primes, then this natural number would be half of that even number, and the two primes would be placed on either side of that natural number. So this is working like this because 7 times 2 is 14, and 14 is 11 plus 3 from the Goldbach conjecture. 18 times 2 is 36, and 36 is 23 plus 13 from the Goldbach conjecture. So the Goldbach conjecture would basically imply that for any number, you have two primes on either side of it. Equidistant. Any questions on that particular statement, or did that completely fly over your head? It took me quite a while to make sense of it. I actually made sense of it when I was taking a walk way back in 2019, I think December. I was just taking a walk outside my grandmother's house, and I noticed that there were pavements on the sidewalk. So I kind of stood in between two partitions of a sidewalk, and I assumed if I was the natural number, I should have two primes on either side of me. It kind of made sense when walking on the road, right? I thought there's one prime ahead of me, one prime behind of me, and both of those primes will add up to form the even number, which is twice of me. I have a message in the chat. So, sir, can we tell that we have natural number and it can be written as P1 minus P2, and there are infinitely different ways to write P1 minus P2? Yes, in a sense, but that is not exactly what we're implying. We are saying that you have two primes on either side of the number. Doesn't mean that if you subtract the two primes, you'll get that number. You don't have to get that number. The two primes might just be one away from the number, right? The number might be 6, so you have 7 and 5. 7 minus 5 is not 6. It is just talking about the fact that for any natural number, you'll have two prime numbers, at least two primes. It could even be multiple pairs, but you'll have at least one pair of primes, one ahead and one behind, equidistant from the number, because only then those two guys can add up to form that even number, which is twice of this natural number. Okay, that I hope that made some sort of sense. So now let us continue with our paper. This was basically the first line of whatever I was reading out to you. Okay. So the popular Goldbach conjecture is equivalent to the following claim. Okay. So what is the claim? For all x belongs to n, basically, so implying for all natural numbers. Okay. This statement says for all natural numbers, there exists, this symbol means there exists, an m is also a natural number, such that x plus m and x minus m are both primes. So basically, when you say that two primes should be equidistant from that number, you're saying that there exists another number which you can add or subtract to get primes on both sides. Okay, let me read it again very slowly. The popular Goldbach conjecture would be equivalent to the following claim. For every natural number, there exists another natural number such that you add the two natural numbers or you subtract the two, you will get primes on either side. Okay, so note that x need not be an even number. X can be odd. That doesn't really matter because when you're multiplying it by 2, it will anyway become an even number. So the existence of primes on either side of it implies that 2 times x will be a sum of those two primes. That's exactly what I explained to you right now. Okay, so now let us see what my conjecture is. Let us define a function f of x, a capital F of x. Okay, so we are defining a function on natural numbers. I hope all of us are clear with the definition of a function. So we define a function f of x such that for all x belongs to n, that's all natural numbers. This is just a fancy way of saying for all natural numbers. We define f of x to be equal to m, where m is the smallest number such that x plus m and x minus m are both primes. So basically, once you get your x and the m, both of those, what you define here is you define a function. So for each of those natural numbers, you give the function value to be that m which you should add or subtract to get those both primes. And you pick the smallest such m. So going back to our example, if we are talking about 7 as my natural number x, what would be the m that would give me primes on either side of 7? Any answers to that? Put it in the chat. What would be the m that I can add or subtract to 7 to get two primes on either side? I need a natural number. Yes? Good. 4. 4 is the correct answer. So 4 would be the smallest such natural number. Okay. So 4 is probably the only natural number, right, which you can add and subtract from 7 to get two primes. So f of 7 would be 4. This is the function that we are currently defining. Okay. It's the smallest number such that x plus m and x minus m are both primes. Note that with each m, we get a unique way of representing 2x as a sum of two primes. So our function will only pick the smallest m. Okay, it doesn't mean that is the only possible solution. Now, if for example, if I pick the number 12, okay, I could define m to be equal to 1 because 12 plus 1 is a prime, 12 minus 1 is a prime. So m is 1. So f of 12 will be 1. There might also exist another number which I can add and subtract, which could be 5 because 12 plus 5 and 12 minus 5 are also primes, but that will not be my f of 12 because f of 12 is the smallest value. So some examples, f of 6 is 1 because you do 6 plus 1, you get 7, 6 minus 1, you get 5. F of 15 is 2. 15 plus 2 is prime, 15 minus 2 is prime. Okay. So thus f of x indirectly gives us the solution to 2x as a sum of two primes which has the closest primes to each other. So let's slow down a little bit. The goal here is once you define this function f, now you can pick 2x, which will be that even number, which was actually the sum of those two prime numbers, correct? And because you're picking the smallest possible number which you can add and subtract, you're now getting two primes that are closest together, which add up to form that even number. So you're getting a solution to the Goldbach conjecture using two primes that are very close to each other because you're picking the smallest possible m. If you had picked the largest possible m, then you would get a solution which would be two primes which are furthest away from each other. Okay? Is this making any sense? At all? Or is it confusing? Does anybody have any question at this point about the definition of that function and what exactly it is giving us? No? Okay. Now let us just look at this graph over here, where what I'm doing is I'm picking an even number and I'm plotting f of x. So picking a natural number and plotting f of x. So here we have all our natural numbers, and here it's just plotting what that m value will be. What will be the smallest m value that you can add or subtract to get primes. So which was our example? For our example, f of 6 was equal to 1. So let's see if that somehow fits in here. So maybe 6 would be somewhere here, and I would have f of 6 equals 1. So f of 100 would be something over here. So this is like a very detailed, it's not extremely detailed because we have too many numbers here. But what it's basically plotting is on the x-axis, you have the natural number. On the y-axis, you have that m which you should add or subtract to get primes. And the smallest such m. And the conjecture is that the peaks of this function, the record holding, so the highest value will always be a multiple of 3. That is the conjecture over here. So the m value is pretty random, right? It goes up, goes down, goes up, goes up. But each time the previous record is broken, you get a multiple of 3. That's what that conjecture claims. Somebody has a question. Yes, Anirudh, can you unmute and you can ask me?
Yeah, so in the start, when we were actually discussing about Goldbach conjectures, you had actually stated that there were two places or two numbers where the Goldbach conjecture does not work.
That is the Goldbach's weaker conjecture.
Yes, in the Goldbach weaker conjecture. So supposing I take those two numbers and try to put it in this graph, what will happen to the graph? Will it remain the same? Will there be a solution interval, or
those two numbers are not connected to this conjecture at all. Those are numbers which cannot be written as a prime plus twice a square. Here we are talking about even numbers being split as a sum of two primes, and we are trying to see how far those two primes can be apart from each other in the best case scenario.
Okay, if nothing will change at all.
Yeah. So those numbers will probably not make sense over here because they are random numbers. They don't have solutions to the weaker Goldbach connection. They have nothing to do with the stronger Goldbach connection. Okay, so the problem here, the conjecture here is that these peaks, so peak is defined as something that is more than anything before it, will always be a multiple of 3, the m value. So what that would imply is that if you were to look at all Goldbach solutions to all even numbers where you pick the best possible solution, meaning the primes that are closest to each other, and you looked at their difference, each time the record is broken, it will always be a multiple of 3. That's a little bit of a crazy thing. So, I mean, I'll explain it a little more clearly and then we can wind up for today. This is a very heavy material. We can discuss about this once I stop recording. How do I define these peaks and how I can study them in a better way? I define another function g to just keep track of. So what is this g of x doing? So g of x will give you the maximum value of f of x for all x smaller than your number. So you'll just talk about, so suppose I was defining g of 20, it will look at f of 1, f of 2, f of 3, f of 4, all the way up to f of 20, and it will tell which had the highest f of x value. That will be g of 20. So g of x is basically a step function. It will only change when the record is broken. Otherwise, it will remain constant. So let's suppose, so here I have f of 6 equals 1. Then I'll find f of 7, f of 8, f of 9, f of 10, whatever. But g will not keep increasing or decreasing or whatever. It will just either stay the same or it will suddenly jump up once the record is broken. Then again, it will stay the same. Because it's basically looking at, so let's read this out, such that for all natural numbers, g of x is defined to be the maximum among all the f of n's for n smaller than x. So n is also a natural number. So what we take is we take all natural numbers which are smaller than our initial natural number, and we take the largest f of that natural number value. And that will give us g of the starting natural number which we wanted to calculate that for. So what that would imply is that g of 10 would always be greater than g of 9. G of 25 would be greater than g of 10. G of 30 would be greater than g of 25 or equal to. It can never be smaller. It's a strictly equal or increasing function because it is taking the maximum value up to that point for f of x. Does that make sense to any of us? You just look at all. So here we have this graph, right? F of x, all this graph. But this is basically plotting f of x for each value. What we will do is rather than plotting it for each value, for g of x, we'll only plot it once the record is broken. Rest of the time, it will remain the same. So this is how the g of x function looks like. It's a step function. So it starts like this and it remains the same. Then the record is broken. Again, the maximum value remains the same. Record is broken. Maximum value remains the same. So what the conjecture is saying is that each of these g values is a multiple of 3. Because g values only take place when the record is broken. And I'm telling you that each time the record is broken, it's a multiple of 3. So it is called monotone and increasing. What is monotone and increasing? It's either going to stay the same or it will keep increasing. It will never go down because g takes the maximum f of x value for everything smaller than your starting number. Okay, so that is my first big conjecture in this paper, which says that for all numbers x which are greater than 8, so I have some small starting criterion because it might not hold true for everything, g of x will be a multiple of 3. That's basically the conjecture at this point. Okay, so that's the first conjecture that I will be discussing in this paper, and these are the graphs that show that particular conjecture, but it has been verified computationally up to, see, I've said beyond tens of millions, and there is no exception for any x greater than 8. So the record breaking numbers are always multiples of 3, the gaps for those primes, which add up to form the even number, which is a solution to the Goldbach conjecture. Okay, so that is what I wanted to discuss for today, and you can ask me more questions, but I'll currently stop the recording.